Good morning. It is October 15th. Uh, over the last week, we've covered a brand new topic in Chem 1A, i.e. chemical kinetics. Last Wednesday, we started chemical kinetics, and most recently on Monday, the 13th, we finished chemical kinetics with our discussion on integrated rate laws. Now, if you recall, I had some technical issues on Monday that prevented me from teaching my normal method, aka via tablet and Zoom, that forced me to resort to the board. Now, I'm not going to bore you with all the details, but ultimately the issue just came from me not updating my iPad correctly and it being incompatible with the latest version of Zoom. Just to kind of reset everyone, especially if the onboard lecture didn't quite mesh with you, because it did throw me off. I just decided to go ahead and re-record a brand new lecture on chemical kinetics and integrated rate laws as a whole. So let me just go on canvas right now. As of right now, there is a lecture recording for lecture 12. Lecture 12 was on October 8th, and lecture 13 was on October 13th. So 2 days. We only have one recording, day one of our 2 days. This is going to be a brand new recording that covers both days. So it'll be a one-stop shop for all of your chemical kinetics and integrated rate laws needs. Of course, by nature of this being a new recording, I'm not lecturing to students. The pacing, I think, will be a lot better. So if you didn't quite mesh with the onboard lecture during those days, then I do recommend you watch this video in full. Not only does it present the same material in a much more visually cohesive manner, I will be going over different questions than what I did during lecture. So this is, of course, a beneficial video for everyone, not just if you attended in person or not. Like I said, this single recording will replace both lecture 12 and lecture 13. It will be a one-stop shop for everything related to chemical kinetics. To jump right into it, I'm actually going to go ahead and turn off my camera, and I'm going to transition to sharing my screen via GoodNotes. Let's begin. Okay. So let's talk a little bit about chemical kinetics. Now, chemical kinetics can be broadly described as the study of the speed or rate of a reaction. Now, up until this moment, a lot of what we've covered can be classified as reaction metrics, aka quantitative measures of a reaction, whether that be mass, volume, molarity. We also talked a little bit about the success of a reaction, aka the percent yield. Today, we'll be talking about the speed of a reaction. Now, to first understand how to discuss the speed of a reaction, the first thing we must understand is the basic principles of collision theory. Now, collision theory is a model that explains the rate of a reaction on a molecular level. On a molecular level. According to collision theory, there are a few basic requirements for a reaction to proceed. Number one is that the molecules must collide. You see, back in module one, we talked a little bit about the different states of matter, solids, liquids, or gases. And we talked about how those molecules, depending on their state, have different motions. Solids are in one place, they're vibrating, they move together as a unit, sort of like a JROTC doing training drills. Liquids have a little bit more motion, and gases are, of course, free to disperse and move around as they want. So there will be some collisions. So for a reaction to occur, the molecules must first collide. Secondly, For this collision, they must have sufficient energy. And finally, the molecules must be in the correct orientation. According to collision theory, these are the three requirements for a reaction to occur. Take, for example, the reaction between carbon monoxide and oxygen gas. Now, if we were to draw this using different colors, what we would see is based on this collision pattern where CO interacts with O2, what we have here is a full-on collision between the two oxygen atoms. Unfortunately, this particular reaction doesn't actually work. However, by simply modifying the orientation, in other words, putting the carbon in front instead of the oxygens, we do in fact see a reaction where we end up with carbon dioxide and a lone oxygen atom. Let me just make this a little bit bigger. What this simple graphic tells us is that the molecule CO was not appropriately oriented to allow for a reaction with the oxygen. In fact, upon a slight reversal where carbon is head on with the oxygens, we do in fact see a reaction leading to CO2 and a lone oxygen atom. This is just one visual example of collision theory in work. Now, all of collision theory depends on a few factors. This is not requirements for a reaction, but just generally what collision depends on. First and foremost, we do need to know what the temperature is of the reaction. We have seen historically that a higher temperature leads to a higher speed. A higher speed, of course, leads to a higher chance or frequency of collisions. What we also see is concentration affects collision, aka the more concentrated a solution, the more molecules there are, the more stuff there is in that solution, the higher the frequency of collision. And finally, the molecular size. This one should be the most intuitive. It's easier to collide with a large molecule than a smaller molecule. Now, all of this together leads to our discussion on exactly what reaction rates are. You see, the rate of a reaction has a very simple definition. Rate is equal to the change in concentration of a substance divided by the change in time. This, of course, can be written as simply as a change in molarity, concentration being molarity, and the change in time. Now, I'd like to point something out about time. As the unit of measure, time is just, well, time. This time could be in seconds, minutes, hours, or even days. It just depends on the context that we're referring to. By most of the cases that we will see in class, it will be in seconds or sometimes minutes, but it just depends on the context. So taking this concept, let's draw what we expect a traditional reaction to look like. Make this a little bit bigger. Now, as the reaction progresses, aka over the course of some time, we can actually model the change in molarity or concentration. What we do see and what we expect to see is at the very beginning of the reaction, the very, very start of a reaction, we have a high concentration of reactants at the very, very start, that instantaneous 0, 0, 0 split-second start, high concentration of reactants. Similarly, at the very beginning of the reaction, we expect and do see very low amounts of product. In an ideal world, it's a perfect zero because at the very, very start of the reaction, no products will have formed. And over the course of the reaction, what we see is this. We see that the reactants decrease in concentration, and we see that the products increase in concentration. This tells us something very important. Number one, it tells us that as a reaction progresses, the concentration of the reactants decrease. Similarly, as the reaction progresses, the concentration of products should increase. Now, this makes sense. As the reaction progresses, you use up the reactants and you form the products. So by the end of the reaction, we are expecting high amounts of product and low amounts of reactant. Now take, for example, with this particular graph, let's just propose a question. In a reaction, the word reaction is here abbreviated to RxN. The concentration of H2O2 decreased from 1 molar to 0.5 molar over the course of 6 hours. The question is simple. Calculate the rate of decomposition. So we don't need too much context for this particular question. We don't need to know too much about the details of the question or the reaction. All we're being told is that a chemical is changed by some concentration over some time. So we can use the formula we just talked about that says rate is equal to the change in concentration, specifically talking about H2O2, divided by the change in time. The change in concentration is equal to the final concentration minus the initial concentration, all over the final time minus the initial time. This is the change. That's what the delta sign means. It's change, the difference between the final and the initial. We see here that we have on top 0.5 minus 1, all over 6 minus 0. Remember, the way how the question is worded, it says it decreased from 1, meaning this is our initial concentration, to 0.5, which is our final, over the course of 6 hours. What we get here is negative 0.083. Now, of course, this putting into our calculator returns this number, but I want to talk very quickly about this negative sign. The negative sign, of course, comes from the fact that we are subtracting a smaller number from a larger number. But does this make sense? It does. Why? Because the reactant is decreasing. And as we saw from the graph, that does exhibit a downward slope. In other words, we do expect the gradient to be negative. So the negative here, of course, is a result of the algebra, but it does make sense within the context of our kinetics discussion. The only thing we're missing now is, of course, our units. Now we know that our concentration on top is molarity, and we know that our unit of time, as defined in this question, is hour. Right? The question did say specifically decreased over 6 hours. If it said over 6 seconds, then the units would be molarity per second. If it said minutes, it would be minutes. If it'd be days, it'd be days. The point I'm trying to make is that the units for time are kind of in flux. It just depends on the context of the question. Now, I'd like to talk a little bit about the classic factors that affect the rate of a reaction. I apologize for my sniffles. It looks like I'm battling a small cold. It probably has to do with the rain we've been getting lately. I don't know about you, but generally speaking, when there's extreme weather changes, I do fall a little ill. Okay. Factors affecting concentration. Now, some of these should be a little intuitive. Concentration, of course. What we do see is that a higher molarity, a higher concentration, leads to more collisions per second. And remember, it's the collisions that really beget the reactions. So as long as we're able to have collisions, we have a reaction. So we want collisions. A higher concentration leads to a higher frequency of collisions per second. Number two, physical state and surface area. Now, in this case, what we do see is the more surface area the substance has, the more collision sites that we see. This simple principle of physical state and surface area actually explains some of the most basic principles in pharmaceutical chemistry. In other words, it's the reason of why we crush medications. Faster relief, of course. The next factor that affects reaction rate is temperature. We talked a little bit about this. We've seen a little bit about this before. So for most of us, this shouldn't be a surprise. A higher temperature leads to faster molecules. And of course, the faster the molecules, the more likely we have collision. In fact, historically, it's been seen that just a simple 10 degrees Celsius increase, just 10 degrees, doubles the rate of a reaction. We can see this, of course, in cooking. It's one of the biggest reasons why we refrigerate food. It slows down the spoiling process. The next factor that affects rates of reaction is known as catalysis. Now, if you've ever taken a biology class, you may have heard heard about a catalyst before within the context of enzymes. But the strict definition is a catalyst is a substance that increases the rate of a reaction without being consumed. What does this mean? This means that over the course of the reaction, it is used and recycled. In other words, it is not used up. It is not completely finished by the end of the reaction. You do expect it to just be present throughout the entire process. The way how catalysis works is that it actually provides an alternate pathway. Now, to get a little better understanding of what this means, we can draw a graph. And we can plot that as the reaction progresses in terms of time, we can map the change in energy. At the very beginning, we see that we have our reactants. And at the very end, we have our products. Now, what we traditionally expect is for there to be a hill for these reactants to overcome. I liken it to a hike. That the reactants must walk up the incline to get to the highest point of the hike. And once they get to the highest point of the hike, it's just a downhill battle all the way to the parking lot. This one is our uncatalyzed reaction, aka no catalyst present. If we were to have a catalyst, what we would instead see is a lower barrier, aka the gradient or the tallest point is no longer the tallest point of the hike. It provides an alternate pathway that's easier to overcome than the uncatalyzed pathway. This is the basic principle of catalysts. Now, I just mentioned earlier that you've probably seen catalysts within the context of biology. So we do have biological catalysts. These actually take the form, what we know as enzymes. We won't need to go too much into this. All we need to know is that biological catalysts, enzymes, work in one of two methods, either the lock and key method or via induced fit. And that takes care of our primary background of chemical kinetics. By understanding how kinetics studies the rate of a reaction, we first understand what collision theory is and how collision theory works. Similarly, we're then able to discuss reaction rates and how that leads to mathematical calculations and quantitative measures of a reaction speed. We then talked qualitatively about the different factors that affect reaction rates. That, of course, led us to catalysis. At this point, we have covered everything that we covered on October 8th, Wednesday, October 8th. That was the same day as the statistics workshop that I had my teaching evaluation. I'm now going to move on to the material we covered on October 13th, that is on the Monday, the lecture that was not able to be recorded. Now we're talking about integrated rate laws. Okay, so let's look at a somewhat generic reaction. Again, I'm using RxN. For the generic reaction, A plus B gives us C plus D, where the uppercase letters represent the chemicals and the lowercase letters represent any stoichiometric coefficients, whether it's 1 to 1 to 1, 1 to 2, 3 to 2, all that stuff. We're able to say that the rate law for this reaction is equal to some constant K multiplied by the product of the reactants, each raised to some number. We know a couple of these already. We know a couple of these pieces already. We know, for example, that the square brackets refer to concentration, aka molarity. We have introduced K, which we will define as our rate constant. And then finally, we have X and Y, which are described as the order of the reaction with respect to each reactant. Here I've abbreviated with respect to WRT. X and Y are the order of the reaction with respect to each reactant. Now, I want to point something out. X and Y are not the stoichiometric coefficients of the chemicals. They are not. In fact, the orders of the reaction ultimately reflect the sensitivity of the reaction, or rather of the rate, by that chemical. For various reactions, we see various rate laws. We're going to go over the common rate laws that we will expect to see in this course. There are 4 types. There is the 0th order reaction, whose rate is defined as just K. There is the 1st order reaction, which is defined as rate is equal to K multiplied by some chemical. Then we have 2nd order, which takes on the form of rate equal to K times some reactant squared. Now, notice that in all of these cases, the type of order has a direct correlation to the power of the exponent. Squared means it'll be 2nd order, to the 1 means to the 1st order. And although not written, you could technically write Ka to the 0, where anything to the 0 is equal to 1, such that this is a 0th order reaction. Now, for the 0th and the 1st order reaction, those cases are simple. You either have some reactant to the 0 or some reactant to the 1. In the case of the 2nd order, the most common one, of course, is this to the 2. But there is another option. What if you have 2 chemicals, A and B, that are each raised to the power of 1? In this case, what we see is that we have orders of the reaction with respect to each reactant, 1. We're also able to say that the overall order is equal to 1 plus 1 equal 2, aka the overall order is the sum of the order of the reaction with respect to each reactant. Yet again, we see here that the complete sum of powers is 2. That's what tells us we have a 2nd order reaction. The last one that we will encounter is known as the 3rd order reaction. In this case, the rate can be defined as K times some reactant cubed. It could also be rate is equal to K multiplied by 3 reactants, all raised to the power of 1, where the overall order is 1 plus 1 plus 1 to give us 3. Or we could get some weird random variations, such as 1 reactant is raised to the power of 2, and another reactant is raised to the power of 1, where again, it's just the sum of the orders. So now a very good question is, how do we determine the rate law of a reaction? Rate laws. Well, the simple answer is through experiments. You see, the thing about rate laws is that although we've studied it and can study it in theory, the simple truth is we need actual data. We need actual information to understand what the exact rate law is of a reaction. So taking a very simple question, it says for the reaction between NO gas, O3, which is ozone, we end up with NO2 plus O2. The reaction is balanced as written. And the question simply says, provide the rate law based on the provided table. All right, let's quickly draw that table up. There'll be 4 columns and 4 rows in total. We have the trial, we have the concentration of each reactant, NO and O3, and we have the rate, which is defined as molarity per second. We have 3 trials in total, of which we have different concentrations. We have 1 times 10 raised to the negative 6, 1 times 10 raised to the negative 6, 2 times 10 raised to the negative 6, 3 times 10 raised to the negative 6, 6 times 10 to the negative 6, 6 times 10 to the negative 6, 6.6 times 10 to the negative 5, 1.32 times 10 to the negative 4, 1.32 times 10 to the negative 4. Now remember, this is not necessarily a table you would be able to determine yourself. It has to be provided to you. This represents actual experimental data for the following reaction given. Now we're able to say that the rate of the reaction is equal to some constant times the product of the NO and the O3 concentrations, the reactants. What we don't know right now, to be very specific, is we don't know what K is, and we don't know what the orders of the reaction are with respect to each reactant. That's what we're going to have to calculate. See, the question simply said just provide the rate law. Okay, that means that our final answer is going to be some form of this equation. We just need to fill in exactly what K, X, and Y are. Here's how it works. Let me just move this over so I have space. Ultimately, what we're trying to find is an expression that looks like that. We need to solve for K, X, and Y. Here's what we're going to do. We are going to pick 2 appropriate trials and compare them. How do we know which 2 trials to pick? You see, we are going to pick 2 trials. We're going to evaluate each reactant. We're going to pick 2 trials for each reactant such that only the reactant under investigation changes, but not the other reactant. What does that look like? Looks like I'm running out of space. Let me just copy this over onto the next page. Right? So just picking over here, we're looking at NO. Looking over here, we're looking at O3. So which 2 trials do we pick for NO? So remember, we're looking for 2 trials where the NO changes and the other reactant stays constant. Looking at the given trials 1, 2, and 3, we're looking for 2 trials where NO changes, so not 1 and 2. We do see here that 2 and 3 has an example where the concentration of the NO changes, but not the other reactant. Here's why we pick these 2 trials. Since the O3 is constant, any change in the concentration leads to a change in rate. What does that mean? Let's look at it again. Again, in trials 2 and 3, O3 is constant, so there's no difference. So any change in the 2 rates has to be because of the change in NOs. So in the case of NO, we're going to pick T3 and T2. What about O3? So again, the same logic. We'll be looking for 2 trials where O3 changes, but not the NO. Doing a quick scan, we actually see trial 1 and 2. The O3 does in fact change. the NO does not change. In other words, any change in the rate has to be because of the change in O3. That's why we will be picking trial 1 and trial 2 for O3. What we're going to do now is we're going to compare both. Convention to put the larger value on top. In the case of T3, the concentration for T3 is 2 times 10 to the negative 6. So we'll put that number on top, divided by 1 times 10 to the negative 6. We know based on the concentrations, we know the rate's 1.32 times 10 to the negative 4 divided by 1.32 times 10 to the negative 4. Where did I get these values from? Well, remember, we're looking at trials 3 and 2 for NO. We know the rate, we know the concentrations, the 2 and the 1. We also know the rates, 1.32 and 1.32. It doesn't really matter which one is on top, T3 or T2, or it could be T2 over T3. The simple truth is conventionally, we like to put the larger concentration on top because it avoids us having to deal with fractions. So we're going to put the 2 on top. That's what tells us T3 is on top. We calculate these values. Over here on the left, when you divide the 2, that's 2. Over here on the right, when you divide that, that's 1. What we're going to do now is we're going to reduce these numbers to a power of 2. 2 to the 1 is equal to 2. And 2 to the 0 is equal to 1, because anything raised to 0 is 1. This is what tells us that the order of the reaction with respect to NO is 0th order. You see, some variation of it will always lead to 1 over here on the right. We just need to reduce the 1 over here on the right. Sorry, over here on the left, it will be always some variation reducing to the 1. The question is, what's over here on the right going to be reduced to? In this case, we can see that when the concentration is doubled, nothing happens to the rate. Since nothing happens to the rate, this is a 0th order reaction. In other words, the concentration of NO does not affect the rate. Let's try the same logic to the O3. We're using trial 1 and trial 2. We put the larger concentration on top. It looks like trial 2 is going to be on top. So we're comparing trial 2 over trial 1. We have here 6 times 10 to the negative 6, all over 3 times 10 to the negative 6. We know based on the rates, that is 1.32 times 10 to the negative 4, all over 6.6 times 10 to the negative 5. Same thing again, we put it into our calculator. Over here on the right, we get 2. Over here on the left, we get 2. Over here on the right, we also get 2. We can continue to reduce this to powers of 2, 2 to the 1, 2 to the 1. Yet again, on the left-hand side, we do get some variation of to the 1. So the right-hand side, just as over here, tells us the order. This is a 1-to-1 ratio. This is actually what tells us that the reaction will be first order with respect to O3. Another way to put this is that when the concentration of O3 doubles, so does the rate. That is a 1-to-1 ratio, a first order ratio. Now, so far, according to our calculations, we've calculated the order of the reaction with respect to each reactant. All that's left is to calculate the rate constant. To calculate the rate constant, we start with our equation. Rate is equal to K times NO to the 0 multiplied by O3 to the 1. Where did I get those numbers from? Remember, that's what we just determined up here, the orders. The order of NO is 0th order, so the power is 0. The order of O3 is first order, so the power is 1. We can actually rearrange this equation to say that to get K alone, we divide both sides by NO and O3 raised to the respective powers, such that on the right-hand side, these two are canceled out, such that we're left with K is equal to rate all over NO to the 0, O3 to the 1. All we've done is just manipulate the rate law expression based on the orders that we had. Now, at this point, we can actually make it a little simpler. Anything raised to the 1 is itself, so we don't need to explicitly keep writing the 1. And anything raised to the 0 is equal to 1, so we actually don't need to explicitly write this in. So we see here that in this case, the rate constant is calculated as the rate divided by the concentration of O3. So what do we do? How do we know what to use? Well, don't forget, you were given a table of O3 concentrations and of the respective rate for those concentrations. So the simple answer is you pick a trial. There are 3 trials to choose from. In theory, the rate constant is a constant. It's the same regardless of which trial you pick. So it doesn't matter which one you pick. I'm just going to arbitrarily pick trial 1, here represented as T1. This is equal to 6.6 times 10 to the negative 5. Where did I get that value from? That's because trial 1's rate is 6.6 times 10 to the negative 5. All over the concentration of O3, which is 3 times 10 to the negative 6. Where did I get that number from? That is the concentration of O3 in trial 1. So like I said, you have 3 trials to pick from. I just arbitrarily picked trial 1. Put this into our calculator, we get 22. Now, how do we know what the units of this reaction are? Well, let's take a look at the respective units. So we see here that rate is molarity per second. How do we know that's the rate specifically? Because it's defined to us in the equation in the table. And we know in general, the units for concentration is just molarity. Mathematically, what this tells us is that the molarities cancels out and we're left with per second. That's how we know that the units of this rate constant is per second. What this overall tells us, now that we have everything, remember the initial question was to put it in this form. Rate is equal to some constant multiplied by the concentration of NO multiplied by the concentration of O3, where they're each raised to their orders. After solving everything, we now know the rate law expression is rate is equal to 22 per second multiplied by O3. Remember that we calculated the order of the reaction with respect to NO is 0. Anything raised to 0 is 1, so that can be eliminated. We calculated the order of the reaction with respect to O3 is 1, and anything raised to the 1 is itself. So here we have our final answer. Rate is equal to 22 seconds and O3. Now, this is just a quick example of one sample question. How to determine the rate law, how to use it, and how to all that stuff. We see here, this is a case of both the 0th and the 1st order. This leads us to our table of information regarding various rates, their orders, their equations, and the like. Now, this table right here tells us a couple of things. It tells us for each order what their rate law is, what the graph looks like, the half-life looks like, and what the units of K. We talked about in class, we've already gone through a couple examples. You had a little bit of time working on a workshop. So you can continue to practice now that you have a formal lecture on chemical kinetics and integrated rate laws. And over this recording, I will remind you, this table will be provided to you except for the graphs. Meaning you do not need to memorize the rate expressions, the half-lives, or the units. They will be provided to you, but you do need to memorize the graphs. Because I could ask you in a sample question, just as we did on the workshop, please provide a graph for the reaction based on the calculated order. Okay. So in sum, that's pretty much an abridged slash abridged and comprehensive don't quite make sense together. Um, we have here a complete lecture on both kinetics and integrated rate laws that replaces both the lectures 12 and 13, October 8th and 13th. We've already had some time with workshop practice, so a lot of this material should not be inherently new to people, but it should be a little bit more visually cohesive and understanding such that you're able to practice the questions on your own. If you recall, I'm showing on Canvas, the worksheet's already posted online. We did the first question in class, the one with NO and H2, and the workshop, we assigned question 2, the N205. And then we assigned some questions as extra credit. I don't remember exactly what I said. I think it was any 2 questions. Any 2 questions from the set is the extra credit. And you must do all parts. As always, if there's any questions, feel free to reach out to me. I'm always happy to help. Have a good day.